lecture. I mean, we can't wait too much here. So I did start the recording here. And we start on the talking about the periodic table and about the start to the different of the groups. And if you look at the whole groups here, we have the groups are coming from the top to the bottom. Those are columns. The periods are those rows from the left to the right. So if you look at the whole groups, you have 8 groups. You have how many? 8 groups. A means main groups. Those are old namings for the periodic table for the groups. Now you will see what from 1 to 18. You have 18 groups in the modern periodic table. You have 18 groups. But in the old namings, which is we go back and forth between those two namings, we have 8 groups. I like this one here, the old one, because the old one will tell me more about the physical and chemical properties of the elements. So we have A and B groups. A is the main groups, and B as the transitional groups. What's the difference between the A group and the B group? Well, the A groups are groups, they have certain charges. They have very fixed charges. They don't have multiple charges. And the B groups, called transitional groups, they have multiple charges. They appear in the nature with very colorful structures. So they are very colorful powders or crystals. So that's the B group. So if you look at this, and I can share this with you here, with the share here now. I will share this one here with you. Okay, I'm sharing this one here with you so you can see the main groups. The here. So these are trying to get this one here working. Sometimes it does not want to work. So those are main groups. Those are main groups. And those here too are fit really inside on those lanthanide actinides. They are taken away out, but they're really compressed inside those groups. So, and the B groups, those are A groups. And the B groups, those are these groups. And what did I did? This one is not correct. Let me take this one here. This one here is a main, considered as a main group, because there's within those groups here it is. Let me see. It is. This is main group with theirs, and this is A. And if it will allow me this or not, I don't know. Yes. That's a B. So the A group is characteristics that they have fixed charges. Some of them, they have very rare multiple charges, but mostly they have one charge. They don't carry too many, but there are exceptions. The big groups, they have too many charges, and therefore they appear inside the nature with a colorful structures. So they have very nice colorful structures. The metals inside the periodic table is almost like 75 to 80% of the elements. The majority of the elements are metals. So all those here, guys, all those are here are metals. Here, aluminum, gallium, metals, 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 metals. All those are metals. Here, all those are metals. So, and here, metals. So you see about 75 to 80% of the elements are metals. The non-metals are just very few of them here. I have another color for them. Those are, and the hydrogen here. So those are non-metals with yellow highlight. So those are non-metals. And the metalloids are the one with the orange here, with the stairs here. Those are 2 and 2 and 2, 6, 7, and 8. Those are called metalloids. Now, the question is, what's the difference between the metal, the non-metal, and metalloids? Well, it turns out to be metalloids. There are elements that they can show the characteristics of a metal in some conditions, and they show characteristics of non-metal in some conditions, the other conditions. So metalloids, they're flipping back and forth between metal character and non-metal character, depending where they are put in, what condition you are using on them, they can act either or, metal or non-metal, right? The difference between the metals and the non-metals, those the yellow one and the highlighted red ones, the metals are the first characteristic, the most striking features is the conduction of electricity. So if somebody will ask you the exam or any quiz, or just ask you, you say metal and non-metal, what's the difference between them? Well, it turns out to be there are major differences between them, and the most striking feature is the conduction of electricity. So the metals, they conduct electricity 100%. So the non-metals, they don't conduct electricity. One example, as I said, I mentioned, if I put my fingers inside the power here outlet, I will be barbecued, correct? Really, really barbecued. So because all the current, all the electrons, current means what? Electrons transfer, motion of electrons. They will go through me back to the ground, correct? From whatever they are now going. So they'll go through me, the heat generated, I will be barbecued. So they conduct electricity 100%. However, the non-metal, they don't. We are breathing, inhaling oxygen, exhaling CO2 out. Both CO2, carbon dioxide, and oxygen are made of non-metals. Oxygen is non-metal. It's not conducting electricity. We are not dying, correct? So that's the difference between them. Second major difference is compressibility. Compressibility means if I have a metal, try to compress it, what will happen? If I put a lot of pressure on press metals, try to push pressure on them, you make them, you destroy them, make them useless. Now, the non-metal, on the other hand, they are compressible, means if I have non-metal and I compress this nonmetal. This nonmetal will go from gas to liquid. If I compress further, this gas will come to what? To powder. And this is the characteristics of the nonmetal. Now, another feature. So we said I can compress the nonmetal. I cannot compress the metals. Now, what's the third feature? Well, the third feature is most of the metals are solids. Most of the metals are solids. Now, do we have exception? Yes, we do have exception. We have exception. We have mercury here, which is, let me take this one out. Mercury here. Mercury here is a metal. However, it is liquid. Mercury is a metal, but it is liquid. It is what? It is liquid. So therefore, that's an exception for the rule we have. So this is all the metals, or the majority of the metals, all the majority of the metals are solids. Some exceptions, we have mercury is liquid. Now the non-metals is totally different. We have solids, we have liquids, we have gases, correct? So we have carbon is non-metal, is solid, charcoal, correct? Or the barbecue, charcoal. We have nitrogen, oxygen, fluorine, neon. Those are gases, helium, gas, correct? You go further there, phosphorus is a solid. We have white phosphorus and we have red phosphorus. Those are solid. Sulfur is a yellow powder. It's solid, correct? Bromine, on the other hand, is non-metal. It is liquid. So the non-metals, they can vary. They can be metals, they can be a solid, they can be liquids, they can be gases. But the majority of them are gases, but not all of them are gases, correct? Not all of them are gases. So that's at least will give you the idea about the differences between the metal, the metalloids, and the non-metal. Now the metalloids, about the metalloids here, the unique thing is they have the same, to some extent, compressibility to some extent, conduction of electricity to some extent, meaning your laptop, your iPad, and all this keyboard here, they have copper chips inside. Those copper, those covers like semiconductor. They don't conduct electricity for high. So the metalloids are acting like this. They don't conduct electricity 100%, but to some extent they conduct electricity, but not if you get electrocuted by a semiconductor, you'll not be dead. You'll not be barbecued. You're still alive. You'll be still alive. But if you are electrocuted by a metal conducting electricity, you'll be dead. So that's the difference between them. So the metals of the main groups here, you look at the metals with the main groups, the unique about them, they have in the nature no color. They come in the nature with no color. They, if it's a metal, they come gray. If they are in salt, they come white powder, white rocks, or if the metal, they are gray. However, if you look at this one here, you will see that's the big difference. They come with a lot, the B or the transitional elements, they come with a lot of different colors. So they come with different colors. So this is for this. Let's go back and look at the our PowerPoints. Sharing this. So, and then when it comes to the names, they have, as I said, they have special names. We can go back and refer to ours here. Let me just share with you this one here again. So if you look at this, they have special names. So if you look at the, so they have special names. So the first name here, the first group here, called alkali. Correct? The second group, earth alkali. Alkali means they make bases. They make what? They make base. Not as acids, they make bases. Then you can come here, then they carry the group name of, this is boron, the boron group, carbon group, carbon group. Oh, I see why I'm using the of Snagit, I guess. So anyway, number 6, number 6 carbon, number 4, 5 nitrogen group. And then this is called oxygen, called chalogen. And the number 9, halogens, and then 8, the last one, called inert gases. So it has a unique names. This group here called, it is lanthanides, and this group called actinides. The lanthanides and actinides, mostly their names after the scientists who had discovered them, or the city or the lab they were discovered in. So this is just an idea what's going on with this periodic table. Any other question you have about the periodic table, or we go in depth in looking at this? So those are just the names of the compound. Now we have seen that's the whole thing here, the periodic table. Periodic table is designed with the increasing atomic number. So we have the periodic table. An element is designated by 3 things. An element is designated by 3 things. Let me show you here, periodic table again. Let's go for periodic table here. Here it is, periodic table. I hope it can be shared here. Okay, let me share the periodic table here. This is the periodic table here. And if you look, each element is designated. This one does not have, of course. It's designated by three items. First of all, the symbol. So we have here, we have the symbol. So let me, we have the symbol of the element. The symbol of the element is made of 2 alphabets in general, but it can be 1. In some instance, when there is no agreement, can have 3 alphabets. But very rare to have 3 alphabets, but 1 or 2. The first one has to be capital letter. The second alphabet has to be small letter. So capital letter, small letter, capital letter, small letter. So that's the symbol here. And in the top, if you look like this, those number here, increasing number, those called atomic number. So if I have, let me say lithium, like lithium here. Lithium has in the top I can write it this way, or I can write it this way here. So this is lithium, correct? Look at the lithium. Lithium has a symbol of Li. The first alphabet has to be capital. The second has to be small. Li, lithium, correct? The smaller one, number, called atomic number. Atomic, this one here called atomic number. What that really is number of protons or number of electrons. That's what it really is. In the top, called atomic mass. Atomic mass. What's really represent is number of protons plus number of neutrons. Yeah, okay, can you see that? So each element inside the periodic table has to have a symbol. This symbol is made of one alphabet, like carbon. Carbon is C. Or two alphabets like lithium, Li. The first alphabet has to be by all means capital. The second one has to be small. But if we have a third alphabet, it has to be small. Just one single one will be capital. So you will see some of them, they are not decided yet. You can see here, but I think this is an old, if you look at these guys here, look at this one here, what they say here. Look at those here. Those already decided. When they don't decide about those yet, they give them three alphabets. But if you look at the modern, which is ours, I think they have it already. You'll see those are already named. But this looks like an old in the 80s or something. Those elements are not, they don't have names yet. They are there, but they were there at the time, and they are still there, but the name of them is not given. So mostly of the higher numbers, they are given to the scientists who have worked on them, or the city, or the lab they were discovered in. So, but anyway, so two alphabets or one or three. Three is I said it's very rare, and the name is not there. So now with atomic number is number of the protons. Atomic mass, number of the protons and neutrons. Now, how about in the nature? Some elements, they have more than modification. Carbon has three types of carbon. We call them isotopes. Isotopes is the same element that's found in nature with three different number of neutrons in it, correct? So therefore it's called isotope. So let me go back here. Back here and here. So let's see here. So there is, I'll just show you about the periodic table here. So the periodic table is allowing us from the elements here, we can determine the isotope, the mass spectroscopy allow us to determine the natural abundance of each isotope, of each element found in nature. So if you look at the picture here, let me give you here the picture here. This is magnesium here. So magnesium, if you look at this, the atomic, the mass number is given to you at the bottom. This is the mass number here. Look at this here. Make sure this is, I'm sharing the correct. So if you look at this, this is the atomic number, correct? And this is the natural abundance. It looks like the 24 isotope we have carbon. We have not carbon, we have magnesium. Let me take this one out. We have magnesium dash 24. Magnesium dash 25. And magnesium dash 26. The way we write the isotopes, we write the elements, and then we write dash, and we write the atomic mass. Those are atomic masses. So AM, atomic masses. Those atomic masses, we write them there. So this is the way we can determine the what they call it. We can determine the isotope writing up. So that's the way we can write any isotope. So magnesium found in nature, it has 3 isotopes. Those isotopes, the atomic number of, the atomic mass of isotope 24 has abundance of 78.99%. The second one here, which is 25, atomic mass 25, has abundance of 10%. The third one, 26, has abundance of 11.01. So we have to know what is really the atomic mass appear on the periodic table. How we calculate for each element that has different isotopes in nature, correct? Its atomic mass is 3. Can we take just the average? Average atomic mass is 25 plus 24 plus 26 divided by 3. The answer is not correct. No, we cannot do that. So we have to calculate different way. We call it average weight atomic mass. But before we go like this, I want to ask you a question here. How many magnesium 24? How many protons do we have? So let me we have a Microsoft Word here. Word. Okay, let me pen it for future. Pin to task. Okay, so blank one. Stop sharing here. Okay. Okay, so share this one now with you guys. Share the Microsoft Word. So I have magnesium, and I'll make it bigger. Magnesium, and then in the top here, atomic mass, I'll put the top of it. Here it is 24, correct? And what is the atomic number? Somebody will tell me atomic number, magnesium. How much? 12? Sure is 12? Okay, that's correct. Because the atomic mass always double. In most of the instances, the atomic masses are double the atomic number. So now, you tell me about this one here. Let me insert here. Shape. Okay, so well, we can give it another color here, red. Put the edges. So now tell me how many protons we have here. Protons. B plus. B plus. How many protons do we have here? How many? How many protons does magnesium atomic mass? How many? 12, okay. That's correct. How many electrons? Oops, sorry. Electrons, E. Okay. We said in a neutral atom, the number of electrons equal number of what? Protons. The positive charges of the protons has to equal the negative charges of electrons. So it is what? 12. Correct? So how about neutrons? Neutrons, how we get this one here? N. N has no charge. Correct? Zero charge, no charge. How we get the neutrons? Well, it turns out to be the sum of the atomic masses, which is sum of neutrons and protons, which is 24, correct? Minus the proton number. The protons is 12. Makes what? 12. Okay. I'll make it smaller here. So how about copying the whole thing here? We have the 25. So you tell me, how many protons we have here? How many? 12 does not change. Atomic number will not change, so the proton will not change. The only change is the number of the neutrons. 12. How many electrons? 12. Neutrons, that will change now. 25 minus 12 makes what? 13. Correct? Let's copy and paste the whole thing. So how about if I have 26? So how much? The protons will remain as they are, 12, no change. Electrons will remain 12 as they are. And then I have the 26. 26 minus 12, how much? 14. Now, let me sit down and write the abundance so we can calculate the in the periodic table. Okay. So we said from the lecture here, let me see. We have the 24 is 78.99. So this one here, it is natural abundance. Natural abundance is 78.99, correct? Percentage. This is a percentage unit. So this is this. So the second one, natural abundance is 10, I think. Let me just double check. Natural abundance is 10. Double check. Double check is 10.00, and the other one 11.01. Other one is, so it is copy. Natural abundance 11.01. The question is how to calculate, guys, out of this data here, out of this data, how we can calculate the average. Question is, what is the average weight atomic mass of magnesium found in the periodic table? When I say found in the periodic table, means found in nature as well. So we know that's one. The first one is 78. So the big mistake on the students, they will come to the point because they are weight, average atomic mass, weight average, and then the misleading average here. See here, it's very misleading. So the students will come to the idea. So, okay, so this is average. Let's take the average of the mass of 24 plus 25 plus 25, those atomic masses, plus 26. And then divide them by 3. So common mistake, common mistake. Average mass, atomic mass, be equal to 24 plus 25 plus 26. The whole thing is divided by, here it is, guys, this one and this one here, divide by 3. This is a common mistake by most of the students. So the students will look at this. Okay, those atomic masses, let's add them up and divide them by 3. This is not correct. So this is by all means not correct. So we'll strike this one out. This is not allowed. So this is not allowed. It's not correct. We'll strike the whole thing out. So what we say is correct is you have to include the natural abundance there. So the average weight atomic masses, it is average atomic mass for magnesium. Let me take the strike out here. Will be equal to, it is the 24, correct? 24, the atomic mass of 24, multiplied by its abundance, which is abundance how much? 78.9. This one has to be divided by 100 because it has to be multiplied by 100. So this one here, multiply by this one here, because by 100, so it will be 0.0 point. So you have to divide this one by 100. So this one here multiplied by 7.789 and equal to this plus the 25 multiplied by the 25 multiplied by how much? 10.00. 10.00 is 0.1000 plus the 26 multiplied by 11 point divided by 100, 11.01. So now if you do all this together, you'll end up with the value that's really found in the literature. So if I look at here, I say it is atomic mass of magnesium found in periodic table. So atomic mass of magnesium is given to you to be the value. If you add them up, you'll end up having, the answer is here is 24 is, this is 24.0345, and this is unit called AMU. AMU stands for atomic mass unit. So guys, can you see that here? Can you see the example? You want another example? Another example? Let's look at another example, maybe in the They have another example there. So let's see if they have another example. Yes, they do have another example here. Let's look at this example here together. Look at this example here. This example, it does not give you, correct? It does not give you the natural abundance. See the trick? We multiply the whole thing by natural abundance, correct? The natural abundance has to come up to be 100%. If you look at the example I gave you here, guys, look at the example here. If you add this one here, okay, this one here, the natural abundance, 100%, and which one? With this one here. You add them up, they have to come up to 100% or 1. They have to come up to 100% abundance found in nature or 1. So it's the same thing here. If I can give you the average, but I leave you without the percentage, I mean abundance. But I will give you all the information you need. Atomic masses are there for each isotope, correct? But I'm not giving you the abundance. And you have to tell me how many of those 2 or 3 isotopes are found in nature. What is the percentage of each in nature? And that's what's in the example here. Let me switch to the so let's look at this, guys. I have chlorine atom. Chlorine atom has 2 isotopes. 2 isotopes, correct? The isotopes are not differing in number of protons or electrons. They differ in number of neutrons. So when I look at the isotope, I look at the atomic mass up. I look to this. Here, look at this, guys. I look to the those here. See, 35 atomic mass. The 35 here. And I look at the 37. So now what this 35 means to me? How many protons? How many protons? 35. So how many protons? Well, you have to look at the atomic number first. Atomic number of chlorine is 17. I have 17 of, come on, guys. I know it's too late, but 2 o'clock, but come, work with me a little bit. So I have chlorine. It has 2 isotopes. The atomic number of isotope of chlorine is 17. Here it is, guys. Here, look. 17. 17. 17 means what? I have 17 protons. I have 17 electrons. For both isotope, it does not matter. So they have the same thing. So for the isotope 35, chlorine dash 35 has 17 protons, 17 electrons. How many neutrons we have? How many? 35 minus 17, how much is it? How much? 18. Okay, 18, that's correct. How many 37? I have 17 protons, 17 electrons, 37 atomic mass. How many neutrons I have? 20, right? 37 minus 17 is 20. Now, I did not give you the, that's one of the, long time ago, was one of the ACS exam. They give you the information, but they don't give you the abundance. Calculate the abundance. Well, you can calculate. You assume for 1 is X. The second will be 1 minus X, correct? Because all those abundance has to come up to 1, which is 100%. So let's look at this. So here it is. Let's get X represent this one here. It does not really matter. So X is this one here, correct? That's the percentage abundance. What with the other isotope, you have 1 minus X. So you make the, look at the equation here, you make the average weight with the whole equation together. So the average weight 35 multiplied by X plus 37 minus X. And this value here is given to you here. It's already given to you. So if I look at this, so this value is given to you here. This is from the periodic table. And this from the periodic table, this is average weight from the, it's given to you. So this one here from the periodic table, here it is. And those here, the x's here are, and the x, those are the abundance here. Those are the abundance. Now solve for x. You know how to do that, correct? Don't please come and see me. Please come and see me. So 35x plus 37 minus 37x. You solve the whole thing. X will come up to be 0.775. Correct? So x will come up to be 0.775. 1 minus x will be 1 minus x will be 0.225. When I tell you 0.225, you transfer this one here into percentage, correct? Multiply by 100. This will be multiply. I mean, this one will be 100. This one will be 77.5, and the other one is it is, and the other one is 22.5. Those type of they demand a little bit of attention because it's not direct, but you can still solve them. Now this is the same thing here. Look at this. You have boron has two isotopes. One isotope is 99, correct? With all atoms are 10 boron with the mass of this as atomic mass. And the remaining 81 are 11 B isotope with the mass of this. Find the average atomic mass. Well, the average atomic mass, we talked about it, correct? Is give you the whole abundance. You transfer the abundance into decimal, not 100%, divide by 100. So this amount here, 0.191. This amount will be 0.801. And then you multiply it by the corresponding, its corresponding amount. So the first one here, the 11B, which is the second isotope, has 0.8, correct? And its mass is this. First one has this amount of abundance. Its mass is given to you as 10 point here, it's 10.129. And then calculate them, and then you get AMU, atomic mass unit question. Any question about the isotope and their relative? Any question about this, guys? Any question? Those who came late, I would like to just put emphasis. I would to put the study guide with the questions. They might appear in the quiz and the exam. So we have to go back when we finish this and look at the conversions. I see some students today in the lab, they have some questions about the conversions. We have to look back at the conversions together. So anyway, so this one here is finish all the periodic table. Just we brush through all the information, the important information, and that's what you can expect. This atomic average weight we just went through. This is one of the favorite questions inside ACS exam, inside your final. This question comes almost every semester. Every semester, the ACS people, they love it. They put this type of questions inside. They give you the atomic masses, they give you the abundance, and they calculate. Not with the abundance is unknown, but they give you straightforward. Just you calculate. Don't go to the common average, divide by 3, but you have to multiply abundance for each isotope, multiply by its atomic mass for each isotope. Then the sum will be the atomic mass. So with this in mind, we'll go now from periodic table, we'll go back to chemical formula. Well, chemical formula, we have different types of chemical formulas. Chemical formula, just we said the molecular chemical formula, which will give us the ratio of the atoms or the ratio of the elements within a compound, correct? That's we call it molecular formula. For example, sugar. Sugar is C6H12O6. That's a molecular formula, correct? Then we have this formula here. We can go and look at its structure, its extension in space. So we have the structure formula. Structural formula, those formulas are giving us how this compound is spreading inside the space, inside the 3D dimension, correct? And we have a couple models. You can see them here. We have a compressed one without showing without showing the bonds, the bonding between the elements. So if you look at this one here, look at this. This called space filling. The last one called space filling. Why space filling? It does not show any bonding. It just show the atoms compressed to each other. It does not show the dimension, how they really spread out in space. The second one, the C here, the C called ball and stick. This is by far is the best. Why? Because it does give us the shape, how those atoms, far away from each other and how they extended in space. So they give us the overall shape of the molecule, which is in terms of this compound is tetrahedral. This is a tetrahedral shape, C. I'm looking at structure C. Number B, if you look at the B here, this is structural formula just on the, you are trying to draw 3D molecules in a 2D, in a piece of paper. And sometimes this is very hard to visualize how the whole thing is looking like in a real space. So 2 is a structural formula, which is really is an attempt to draw the 2D in 3D. So this is a piece of paper. So when I write on this, this is 2D, two-dimensional, X and Y. There is no Z towards me. There's no Z. So therefore, this is this Y, this X. There's no Z coming towards me. So, and the second one, B, is called structure formula, which give us just information about the bonding, but does not give us any information about the shape. The other ones, the balls and stick and model is much better, give us the shape. This is C. The molecular formula give us the ratio, the real ratio. So if I have a compound CH4 called methane, I have a ratio of 1 element carbon, 1 to 4 hydrogens. So give us the ratio of the real ratio within the, of the element within the compound. So now we said we have molecular formula, we have empirical formula. Structural formula, I said we are attempting to draw a 2D, 3D in 2D, which is not limited, does not give us that much of it. But then we have structural formula, we guess the exact ratio between all the elements within a compound. That's the molecular formula. Exact ratio between the elements within the formula. How about empirical formula? Well, it turns out empirical formula is the simplest ratio, correct? Simplest ratio of the elements within a compound. The molecular formula is the true ratio, the real true ratio. The empirical formula is just the simplest formula. For example, sugar. Sugar is glucose. Glucose is made of 6 carbon, 12 hydrogen, and 6 oxygen. This is a molecular formula. That's a true relationship ratio between all those 3 elements. However, when I write, I have to make it simple. The common factor between all those are 6. So to be 1 carbon to 2 hydrogen to 1 oxygen. This is called empirical formula, just a simple one. And let me give you an example here. We can look at the examples here. That will give you this example here. This one here, vinegar, for example. Vinegar has molecular formula, the real one, has C2H4O2. That's the ratio between carbon, hydrogen, oxygen, 2 to 4 to 2. What is the empirical formula? Somebody will tell me what's the empirical formula? Divide by the common denominator. So what is the common? Is 2, correct? Common factor of all these values is 2. So divide all those by 2 will turn out to be 1 to 2 to 1. So the empirical formula is this one here. So this is the empirical formula. And this is the true molecular formula. So the ratio is true. But the empirical formula, they are not true, just simplest one. Make it simple, divide by the common one. And here is another example I gave you. I think this is about glucose. Glucose is a well-known example because it has, glucose has the molecular formula is this, as you see here. But when you cut it down, make it simple, it will be 1 to 2 to 1, correct? And therefore the empirical formula will be this. So why we use this? Well, it turns out to be the empirical formula, the simple ratio, are used in the lab to determine the whole molecular formula and vice versa. So, but the main thing is for the empirical formula, we can use it to determine the actual ratio of the to the elements, which is the molecular formula. So that's the importance of the molecular formula. So that's the periodic table. As you see in the periodic table, the atomic masses, see the atomic numbers at the top and the atomic masses in the bottom. Some periodic table, they use the opposite. They put the atomic number in the top, atomic number in the bottom. But the whole idea, if you ask in the quiz or in the final exam, what's the basis of structuring or aligning or arranging all those elements in the side periodic table? What's the basis of this? How we could really align all those elements, arranging them, aligning them one after the other? What's the base for that? Turns out they are aligned and arranged according to increasing atomic number, not atomic mass, atomic number. Atomic what? Atomic number. So atomic number is very important. As you see, the elements are increasing by atomic number, and that's the whole design of the periodic table. According to increasing atomic number, the whole element are designed. And the groups, if you look at the group now, if you have elements of the same group, they will have what? They will have the same what, guys? The same physical and chemical properties. For example, just let me just remind you, a long time ago happened. Group number 1 is no joke. Group number 1, can you see them? Lithium, sodium, potassium, rubidium, cesium, and francium. Those elements are no joke. They can do a lot of damage. And I record this in the 70s when I was in Germany. We have a professor he had overseen our work. So, but he likes coffee, so he goes out 2 doors, inlet and outlet. So we keep 2 people out, and we come and bring all the sodium and the small pieces kept in oil because you cannot keep sodium in the air. What will happen? It will catch the moisture and then give you fire like crazy. So we just put in the sink small tiny elements. Sodium came up all the way, big flame. It was very fun, but very dangerous though. And then we had potassium. We don't have cesium. If we have cesium, we'll burn the whole ceiling. Potassium is so dangerous. We didn't realize if you have potassium and you put it small tiny inside the sink, the whole fire will go all the way to the ceiling and then would spread out like crazy. I mean, so those elements, they react with moisture very vigorously to make hydroxide and to release hydrogen, which is really what is burning in the flame is hydrogen, correct? So imagine you're driving a car and you have a hydrogen tank. That's a bomb. That's a hydrogen bomb, like a hydrogen bomb, nuclear bomb, hydrogen bomb. So hydrogen is not friendly gas. It's highly, highly explosive. So if you put some of those group number 1, we learned ourselves that the physical properties of this element of group 1, they love H2O. They love moisture, they love H2O. So they have to be kept inside the oil. All those groups, we did not have cesium there. I think they were afraid that we might try to burn the whole lab. So they brought for us sodium and potassium, natrium and kalium. In German, they call it natrium and kalium, natrium and kalium. So we put them in the sink, and then all of a sudden we see the flame. So we learned that the physical property of this first group is they love H2O, and they have to be kept inside the oil. If they are kept outside the oil, they'll take the moisture from the air and they start burning like firework, like 4th of July firework. So very dangerous. So that's a good thing. And they're producing a lot of hydrogen, which is burning under explosion. And then you can look at the whole group, group number 1. They are highly basic. If you put the solution after the burning, litmus paper, they make it the red one turns very, very blue. So they are highly, highly basic, correct? So all those groups are grouped together, not the rows, the groups. Meaning what? Meaning those elements, they have to have the same or similar physical properties and chemical properties. And that's the whole clever of putting those elements together in one group. So if I go all the way to the far right, group number 18, for example, or 8A. The group 18 or 8A, those are inert gases. So first of all, inert gases, they are chemically inert. They don't react, correct? They don't conduct electricity. They are compressible, of course, but they are opposite to the group number 1. Group number 1 is very, very active. Group number 18, the end of the periodic table, they really gases. And when you have a birthday or something or celebration, you fill some toys with the helium. Helium is there. Helium is the top. Helium is the top of the group. So helium gas is inert. You can barbecue near it. You can put flame on it. Helium will not burn. Correct. So that's we learned from periodic table. If you put them together, then all the group will behave as such. Will behave the same way. So and each one, if you look at all those groups, they behave within the same group, the same behavior, chemically and physically. So chemically and physically, they're behaving the same. So group number 2, for example, if you look at the group number 2, they found in nature as an element, and they can found in nature as what? As oxides. So those are alkali as well. So okay, so those are transition elements and inner transition elements. We went through these noble gases, halogens, and so let me just look at what we have. Okay, now this is the end of the chapter, about maybe 15 slides. We'll end it maybe by Wednesday. But I have to go back and look at the chapter 1 conversion. Is everyone comfortable with the conversions? Conversions from metric to English, English to metric. Conversions, guys. Anyone is comfortable with the conversions? You know how to do conversions? That will come with you even if you go higher in 1212, because you have to know how to make conversions. If you are working, somebody will work in health-related areas, you have to know, you have to know. When I say to tell you CC, give this patient 55 cc, cubic centimeter. So what is 50 cc, cubic centimeter? 55 cc is 50 mils. 1 cubic centimeter is 1 milliliter. So we have to know how to do conversion, and we have to go back to this. So now we have to go and look at the molecular and ionic compound. So the types of the bonding between those elements within the periodic table, they can combine themselves in two types. I mean, we have other types, but for our purposes, for chemistry, we'll go for two types. We have ionic bonding and covalent bonding. Ionic bonding and covalent bonding. Now we have other types, coordination bonding, for example. That's a third type. We have even other metallo-organic bonding. So that's another other type of bonding. But we are interested in two bondings, the major one, covalent and ionic. So what's the difference between ionic and metallic? Did you hear that in the high school? What's the difference between ionic and metallic? Ionic and covalent. Ionic, and then I'll let you go. So ionic is a bond. Ionic bond is made of a metal, which is combining itself with one nonmetal or more. So at the condition of ionic compound, you have to have a metal present. The covalent, from the Greek name, covalent means to share. There is no transfer of electron, they're sharing. So the covalent is, condition for it, is a combination of two nonmetals or more with each other. So covalent is nonmetals exclusively. And the ionic, you have to have a metal present inside. So that's the difference between those ionic and covalent. So we have still a couple minutes. What is the difference in the physical and chemical properties between ionic and covalent? Somebody will tell me? If I give you two compounds in two bottles, so this compound is ionic, this compound is covalent. How you can differentiate among them, between them inside the lab? What's that? Okay, some covalent compounds, they don't transfer, but some of them they transfer. H2O does not barbecue, but if you have H2O, will be electrocuted. You'll be maybe somebody will get half paralyzed or quarter paralyzed or complete, but you'll not die. But if you have an ionic compound, that's correct. You'll be barbecued. There's nothing there will be left. No half or quarter or whatever. Everything is barbecued. So the conduction of electricity is first, but that's we cannot do it in the lab. We can't put the chemicals inside the current. So what we'll do? Come on, guys. It turns out to be just simple. Put those two out of the bottle, put them in the hot plate. Covalent compounds tend to have lower boiling points. So 50, 60, they start boiling, bubble. Ionic compounds, you need hundreds of centigrade. Even the hot plates will not even catch them. Are you following me? So high boiling points of the ionic compounds compared with the lower boiling points of the covalent. What else you can see? Well, it turns out most of the ionic compounds are what? Most of them are colorful. You see a color there. As soon as you see color, you suspect it has to be ionic somehow. It has to be ionic. It has to be a metal causing this color. And most of the time, your inspection or your thinking about this is correct. Most of the time, 99% Correct. So anytime you see solution is colorful, and most probably will be lab, will be ionic. Now, it does not mean that the covalent compounds they are not colorful. They are, but they are very few. They are not really expanded that much through the lab. I will stop here and then we'll come back. We'll look at some examples. I hope we'll finish chapter 2, and then I'll go back to chapter 1 to go with the conversion. And then I'll give you a study guide. Then you have to study the study guide to study for the quiz. Study for the quiz. Where's the attendance sheet? What's that? No, whenever we are finishing, I'll let you know. Whenever we finish, I'll let you know. And I'll let everyone know. Yes, yes, yes. The main thing is everything connected to time. If you don't study, you cannot, time will be running out. You have to be ready.